So this is a further evidence of the nature of the impact of digital terrain or even clutter on signal propagations. So on the top, you can see a top view of the base station coverage, and in the bottom here you see it's a side view for the reception along a profile for the specific point here. So I'm going to examine the signal propagation from that tower to that position here. And this is what you're looking at here in the profile on the bottom. So let me define first what is what. The gray is the digital terrain model. The base station is on the left. The reception point that I specified is here on the far right. And the green one is the signal level across the journey. So you see how the signal is diffracting right here. There's a significant diffraction at that point here. So when the receiver here go beyond that peak of that mountain, the signal is dropping considerably. Okay, so this is where diffraction model start to calculate signal losses. So if you look at this from search perspective, if you know someone is connected to a tower or was connected to a tower, then you know this area here is all, the red area is useless in terms of search. Okay, so let's continue. So now we're going to talk a little bit about signal propagations or propagation models, especially the deterministic propagation models. Categorically, there are two types of propagation models. We have what we call statistical models. There is what we call deterministic models. So deterministic are based on rules of physics, and they actually use digital terrain and clutter information as a feedback to further optimize predictions. So HTZ philosophy for signal propagation, we divide it into three components. I'm talking about VHF communication. So we break it down into three components. We've got the free space model. So if it is a free space condition, we apply, for example, free space model. If it is non-line of sight, so there's no line of sight, and that's where diffraction hits. Okay, so we calculate diffraction loss on obstacle. For example, here on the right-hand side, the first image you see a single knife edge. So obstacle. So if there's obstacle in the path, then the signal will diffract based on the clearance ratio. Okay, this is the clearance ratio. So how much obstacle is obstructing into the Fresnel zone. And this is the diffraction. So this is a single knife edge diffraction, but HTZ used Dago 94, which is using multiple knife edges. Okay, so this is adding accuracy to the predictions. Now, and also there are cases where you have a combination of line of sight, no line of sight, and near line of sight. So near line of sight is when you have partial obstruction, such as that case in the bottom here. So you've got partial obstruction for the Fresnel zone, and then the tool can calculate the losses due to subpath attenuation. So the bottom line here is that these propagation models are based on rules of physics, and they increase the confidence in the prediction. Because they rely on the environment itself. A more accurate model will produce more accurate predictions. And today, this kind of models or terrain or clutter is widely available to everybody. So this is how the deterministic engine is working. So this is a summary of how propagation works. So let's start by defining these different graphs. So look at the red. The red graph is the signal without diffraction. Okay, or this is your reference model. This is your reference model, like such as free space. So free space is the maximum you can reach. Of course, it's not realistic, but this is serving here as a reference. The green line, the green curve, is the signal propagation along the journey. Okay, so if the receiver is at that point here in the forest here, then the signal level is this. Okay, then when he goes, when the receiver goes to that spot here, for example, is outside the forest, signal is climbing up. So this signal is varying with a variation of the environment, the geometrical propagation. So here the green ones here, the green clutter here, this is a clutter, trees for example, you've got dense trees, you've got light trees. Here the gray is the digital terrain model. Okay, so this is how propagation works in the software. Now let's talk about analysis. What kind of coverage analysis you can conduct, which can be handy for optimizing or the search area. So here we're looking at a composite coverage. This is what we call a composite coverage. So a composite coverage is composed of multiple sites with no discrimination. You can't tell this area, for example. You can't tell who is covering which cell or which sector is covering the area. You can't tell. You can just tell that there is a coverage here. There is enough coverage to have reception. So the gray color is the terrain, and that means also there's no coverage. The blue here means coverage. So this is called the composite coverage, which is combined coverage of all the cells. It just tells you if there is reception or not. It doesn't tell you where the signal is coming from or which cell the target will be connected to. Now this is what we call the best server. So best server is similar. So you see it has the same footprint. The footprint is exactly the same as the composite, but it's using more colors to encode the coverage. So here the dark brown means if a person is connected to, if a person is in that brown area, very likely it will be connected by this cell. The light brown is here on the opposite side. So if someone's connected to that cell, very likely he is in that area. Okay, so this is showing which server or which cell is the dominant in a particular area. And this is extremely useful if you want to know where your target is, because handsets typically hand over to the strongest, to the dominant cell in their area. So if you know someone's connected to this tower, for example, you know you have a massive search area to look after. Okay, if it's connected to this one. If it's connected to this cell, you have a small search area to look after. So the best server is very important because it defines the dominant cell boundary. Okay, and this is what handsets use to in the handover process, and in the camping or connecting to the cell. Now overlap. So we spoke about composite coverage. We spoke about the best server. Now overlap. Overlap is identifying the locations or the areas where reception is possible from two cells, okay, or more. Now in that case I have two cells only activated on the map, just to illustrate this. So you've got two cells, and the pink color is here. Now the pink means overlap, so handset can detect signals from both towers. Both towers can be connected. That's overlap. This is a zoom in. So this is telling me that if someone is being served by these two cells concurrently, he can switch back and forth. Very likely he is located in this area here, because that's the only area or areas where you could get reception from both cells. This is another function that we recently added in HTZ communication or HTZ warfare. This function is called the combined overlap. which is dedicated for search and rescue. So this is the function that further optimizes the search area. So here you can see on the left hand side, you've got two activated cells, okay? And the pink area is the overlap. Pink area is the overlap between these two cells. So your target is somewhere in that pink area, but you can see it's a big area. So by adding the knowledge of the best server or for the non-connected sites, so see the black ones here are non-connected. These are not connected sites. Now the knowledge of the not connected sites coverage, best server coverage more specifically, is going to help us further reduce the search area into this. So you see this coverage, this area here, it is covered primarily or dominantly by these two cells. Now these two cells are not connected. They are not connected, which means you could remove that area from your search area, and now the search area is restricted to these two small patches here. So we managed to reduce the area from, in this particular example here, from 32.3 square kilometer into only 12.8 square kilometer. So this function is actually making use of all the rules of physics, the digital terrain, the technical parameters of the base stations, and making use of the overlap analysis and best server analysis, coverage, and so on, in order to give you a final picture of where the target area or the search area should be. So now let's talk about the system overview. How does the system look like? So initially we were just covering the topics, the concept, and the different analysis and how this information all play together. Now let's look at the overall system. So overall system. So what we designed in this project is the simplified GUI, simple interface that non-technical people can use. Something that they can actually use in a mission critical environment. A simple interface that doesn't ask you too many questions or so many technical inputs. You just want to simplify it. You want to be able to quickly find your area and limit the area of search. So this system relies on information, technical information from carriers and regulator. Now this depends on the country. So every country is different. And some countries, you can get all the technical information of the sites from the regulator. In other countries, maybe you need to rely on some complementary information from the carrier. Now, in this example here with Korea, the regulator is the one making the technical parameters, all the sites, the antennas, and so on, transmission power, frequency available to the agency. But the carrier here is only providing the connected, non-connected sites. Okay, by correlating the IMEI of the handset with the cells. And then you can find out what is the latest or most recent connected cells. So this information are connected using SQL database, in fact. So we collect this information, and then we process this information, and then we can apply some default templates for missing parameters. So some checking for the parameters, some quality checking done by this interface. And then if the information are not within a certain tolerance, then we can apply some default templates, such as antenna pattern, for example, may not be available. So this simplified interface will automatically engage our planning tool, HTZ, does all the calculations or the computations, and then finalize it, and then give you one final outcome in a Google Earth format. So you can, as a presentation layer, you can display, or you can look at the coverage analysis and also the optimized search area. So we're going to rely on all this information. HTZ integration was done using the API. So we're going to talk about this API functionality as well today. So from the regulator or the carrier, we need some basic information, and trust me, it's not hard. So we can get a lot of information from them, and if some information not there, we could use some templates. So we need to have the antenna azimuth. Where is it pointing to? Sector azimuth, the tilting. If there is any mechanical tilt or electrical tilt embedded, we could also capture this information. We need to capture transmission power, antenna gain, transmission frequency, the antenna height, and bandwidth. So this information, we can import them, and we are importing them from a technical database, and then we could model this in a planning tool. Okay, so some of the information you need are site coordinates, transmission power, frequency, and tilting, antenna height, and so on. Now let's talk about automation. So now we're going to focus on this simplified GUI and talk about the sequence of configuration or functions that need to be established in order to produce the final outcome. So it's a 7-step process. Step number 1 in the simplified GUI, location. So first we need to search by address or coordinates. So the idea is that to enter the name of the park, for example, national park, or nearest business, or maybe coordinates. You can put the coordinates directly. So the idea is to specify where is the location, the target location first. And from that location, of course, you can do culling, and then you can do further analysis. So first we specify the location. Second, we can filter by operator. So you can choose what national operators you want to limit your search to. Third, you can do technology restrictions. For example, you want to restrict your culling to 2G or 3G or 4G or 5G. So reduce the number of sites produced in the process. After the step number 4, you need to set the status. So this status could be done automatically or manually, okay, depending on your coordination level with the operators. Usually operators are not very keen to provide API access or something like that. So the idea is that they will give you a list of cell IDs, and they will give you the status, if it is connected or not connected. So this information will be handy. You can update the status of the site or the sites that you know they are connected. Then we could select default templates for missing technical parameters. So the GUI will automatically do some validation, and then we'll use some default templates. So these default templates can be set up for every country or for every operator. That will help enhance also the accuracy, and also substitute any missing parameters. Step number 6, we run the analysis. So analysis, you can you have buttons that you can choose. You can run analysis for coverage, or for server, which is dominant server, for overlap, or for search area directly. Finally, you can export this to Google Earth and then present the outcome. So this is the workflow for the solution. This is how the solution look like. So for the user, that's all what you see. Okay, this is the GUI, and you can do everything from here. You don't need to run a sophisticated tool. You don't need to have a training on a planning tool. You don't have to be an RF engineer to do the job. So that's all what you need to do. So this is in Korean, like I said, because this product was developed for the Korean market. And you can see on the left-hand side, this is where you choose your search, the type of search you want to do. Search by address or search by coordinates. And then here you can choose the operator you want to limit your search to. SKT, Telecom, Korea Telecom, or LGT. And here you can even do also restrictions by technology, 3G, 4G, 5G. So here is your criteria, or your culling criteria, as I like to call it. Here you can do the coverage, you can do the analysis, the coverage analysis directly. You can do composite coverage, best server, overlap. You can do search area optimization. So this is a single button. So you can just click the button you want, and then the software or the solution will automatically launch HTZ, do the calculations, and then present the outcome. And here we have some shortcuts for different type of analysis you could do in the process, like setting up external database and so on. And this is the outcome. So these are the list of sites found in that area. So in that area, we found 1, 2, 3, 4, 5, 6, 7 sites. Okay, so that's the frequency, longitude, latitude, and this is site ID 5330 and so on. And here you can search the table. So you can search for specific cell ID. You can search the outcome for specific cell ID. So you can update the status. So this is the process for culling, which is the first step in the culling. You choose the type of search by address, for example, and then you type the address you want to search, and then you choose the operator. You might want to choose all the operators, and then technology, and then you hit search, and then the software will return the outcome. And then you can go and update the status of that site. You can say connected or disconnected. So you can filter the ones that are connected. So you can filter them and then change the status to connected. Once it's connected, then you can proceed. Once you finish your culling, you finish your status update. Now you can proceed to the analysis directly. So in the analysis, once you click on that button, it will automatically run a certain script or a certain workflow, which will engage HTZ, and HTZ will do all the computations and then present the outcome to Google Earth. It can produce composite coverage for connected, best server for connected, and for best server for disconnected, and so on. So it can produce the analysis for connected, disconnected, and for the search area, and so on. So let me run a demo here to show you how it works. So this is the interface. It's going to search for an area on the left-hand side. There's auto-completion to help you locate the area. This is it chooses not to do any filtering, and then it's returning all the sites. Now he's searching for a specific site name in the outcome. And then you could update parameters here. So it's changing now status to connected. So he found a site which is the victim is connected to. Is updating the status, connected and disconnected. This is giving the freedom also to choose antenna, default antenna from the templates. So now you run the analysis, and you see it will automatically engage the planning tool HTZ, opening the map for the country, running coverage predictions. So this is fully automated. The software will automatically generate the base stations, get the configuration, do coverage computation. So now, after coverage computation is done, it will do coverage analysis, which is the composite coverage, the best server, overlap, and the search area. And it would export this into a TIFF format and to Google Earth, like KMZ format. So you see there's no interaction here between the user and the tool. The tool will just autonomously execute the task. If I speed up this a bit. So now this is the output. So this is the final output. Now we could automatically run Google Earth and then present the outcome, or it could be published somewhere else. So now it's going to add this information to Google Earth to present the outcome. I'm going to run a local example as well to help you further understand this. So this is an example of a project with automation script. So automation script is prepared here. So these execution command lines are usually executed by the application, by the customized application. In that case, I'm just going to run it as a script. So in the output section, I've got nothing here. I'm going to delete everything. So there's no output now. And the input to this is digital terrain over South Korea. And I've got some settings, default settings. And I've got some input such as HTZ. Access database. So I'm going to run the script now. So launching HTZ, importing the sites, connected and disconnected, doing coverage prediction very quickly, saving the coverage, now loading the coverage and doing the computation analysis. This is the composite coverage. So the first one was the combined overlap, which is the optimized search area. Second one is just reception. This is the best server. So all this information, all this analysis are very useful to understand your search area and to prioritize your search area. Okay, this is done. Now let's look at the output again. Here we go. So I'm going to run now Google Earth. So I'm going to drag the KMZs. So you see we have TIFF file, which is generic format, accepted by many JS software. All right, so I'm going to shut down the analysis and then do it one by one. So this is the coverage for the site of interest. This is the coverage, so the reception area. This is the best server. This is the best server. And this is the normal overlap. That's overlap for the 3 sites or the 3 cells in the area. And this is finally the combined coverage, which is the search area. So this is the search area based on the knowledge of connected and disconnected sites. So this is the search area, just the pink, based on the reception. So this was calculated based on the overlap of the 3 cells and based on also the neighboring best server in the area. So let's continue. Now, search area on portable devices. So in fact, you could export your search area or your coverage analysis entirely, which is the best server composite, and so on. You could export this to portable devices or web-enabled devices such as an iPad or a phone or tablet or laptop, whatever. So any device with a web browser, you could actually go and publish that coverage there. So if it's a team, if it's a team working on this, it would be useful, for example, to exchange the coverage in a platform, and then be able to check your location against that search area. So there's a video online if somebody wants to watch it to learn more about this product. So this product is it's controlled by user access. So someone could someone could access the system with the credentials. So I'll show you how it works. So go to the coverage. Here we go. You can search by address. Okay, so you can, it has autocomplete feature. So the different analysis can be automatically added to that tree here, and then you can see the legend here, and you can zoom in and zoom out in the area. So this product is called HTZ WebView. So it's only used to publish the coverage analysis that you produce with the HTZ. It can be published on the web, and they can be available to large audience or to a number of people. So in conclusion, the technical knowledge of the telco sites help optimize search and rescue area. So adding this information or utilizing the technical parameters of telco network can further help you establish a coverage more accurately, and then it can optimize your search area. The tool's complexity and significant inputs can be simplified. So I know there's a lot of agencies, especially non-technical users, have a massive concern about complexity of such tools and the sheer number of technical parameters needed. So this is not a problem. It can be simplified, and it could be packaged in a nice interface with minimal input required from user, and also no intervention. So you could do an interface to local regulator or carriers or local database. So if the exchange between the agency and the regulator or the carrier is happening in an offline fashion, for example, file transfers, database transfers, and so on, yes, this is sufficient. It is possible to establish a format, exchange format, and then that solution can utilize that exchange format to avoid manual process. So for any missing parameters or incomplete parameters, because I know a lot of people or a lot of agencies share that concern, is that telcos or regulators do not keep an accurate picture of or accurate technical parameters of the sites. This is not a problem as well, because usually you have a certain, for example, on a specific band you use specific antenna. Transmission power is usually in a certain range. So it is possible to populate or to complement the technical parameters by relying on templates. So overall, this achieve more accurate coverage predictions. So more accurate cell coverage prediction thanks to the terrain, the usage of the terrain, the clutter, and the propagation engine. It's all helping to further enhance or reduce the search area. So thank you guys for your time. This is for today, for that webinar. And we will be happy to receive any clarifications or questions you might have. Thank you.